think, and I will. So I will, Václav. We will start now. Today we have 3 video sessions, and the first one is Václav Janiš, who is in Prague now, sitting, and he will speak, as you can read, multiple scattering and the many-body Green's functions. So the idea was to combine, to show how the Green's functions are used in the many-body theory, and it's one big important tool. I think some of you people doing GW here, some of them are interested in DMFT. So I think it's that was the full idea of it. So Vasek, you can start. I will turn off the microphone now.
Okay.
So
thank you, Jano, for introducing me. Good morning to Lezuš from Prague, and also hello to other remote participants to this lecture. Thank you, the organizers, for including this talk about multiple scattering in many-body physics, because it's a quite different topic than we heard yesterday. So my lecture is outlined.
Recording in progress.
So I will start to connect with the yesterday lectures and to recall the scattering in quantum mechanics. Can you hear my pointer? Okay, so I can show. I think that you can see it. So that was a short introduction. Then I introduced scattering in interacting particles, which is quite a different topic, as I mentioned. That introduce the green functions and particle interaction, which us need to know, and then how the scatterings can be introduced via perturbation theory. Then the multiple scattering, especially topic, is used as a tool. It's used to renormalize many-body perturbation theory, and I have to introduce irreducible functions which are necessary for that. And then, due to renormalization, I will speak about Baim-Kadanoff as a canonical way to introduce one-particle renormalizations. And also, I mentioned the ambiguity, which is unique for the many-body physics in the relating one-particle and two-particle functions, especially. And finally, I will go to the two-particle approach. It's different from Baim-Kadanoff approach, starting from a different function, and introduce a mean field theory, or mean field-like theory with two-particle self-consistency. The meaning of it, or the importance of it, I will explain. The generating function will be two-particle vectors from which I start in perturbation theory, and introduce a reduced particle equation to describe quantum criticality, its effective interaction, and mean field light approximation, and then at the end, I present how to reproduce or how to calculate one-particle function and self-energies from the two-particle vector. At the end, I short conclusions. Okay. Let me see. Okay. I got lost. Sorry for this. Okay, now. So one particle problem is we have a quantum mechanics, we have a one particle, and the full Hamiltonian consists of the kinetic energy usually, or the one part which can be exactly solved, and external potential, which is usually interaction. The quantum effects emerge also only if the two operators do not commute. That the spectrum of this bare Hamiltonian does not commute with the spectrum, is not the same as the spectrum of the potential. Then, of course, we have to solve this full static Schrödinger equation with a given energy, and we should find this final state, which is governed, the dynamics of which is governed by this Hamiltonian. Since we cannot solve this, we cannot diagonalize this simultaneously these two operators, we have to use some perturbative methods to resolve this problem, to resolve the Schrödinger equation. And now we should distinguish two things according to the energy. The spectrum of the bare Hamiltonian is restricted from below, and the zero is the lowest energy of this Hamiltonian. If this energy lies in the spectrum of the bare Hamiltonian, we speak about scattering states, and energy is bigger than zero, greater than zero. However, if energy is smaller than zero, we can get bound states, which is a different story, and also different techniques should be used to describe. Also, we heard yesterday for Dimitri about what is the problem with bound states and scattering states are combined in three-particle scattering. But the many-body scattering will be quite different from those. However, the important thing is when the spectrum of the full Hamiltonian is not available, so we should resort to perturbative methods, which possibilities we do have. That means we have to split the full Hamiltonian with the bare part and the interaction, and then we solve the bare Hamiltonian. We can find the full spectrum here and the spectral energies, and then we can write this full solution in the form of Lippmann-Schwinger equation, what we also had yesterday, which actually is the integral part or the integral counterpart of the Schrödinger, the differential Schrödinger equation, where here we introduce the boundary condition. That means the plus and minus is a small imaginary, infinitesimally small imaginary part, which defines the plus is retarded propagator and minus is advanced propagator, so backward propagation. And now we see here there's the solution of the bare Hamilton is the full solution here, and it is the interaction. The effect of interaction is contained in this discount is a bare resolvent of this problem. We can go from vectors to operators, introducing the transition matrix, what also Didier introduced yesterday with the T matrix, and we can go from real energies on the real spectrum to complex energies above or below the real axis, which is the resolvent is well defined for any complex energy, and we can try to calculate the transition matrix T matrix as a function of energy. And we see that this T matrix plays a role of the dynamical renormalization of the bare potential. That means this is something what the particle, the scattering states feel during their propagation in this external potential. Of course, we can write this because it's an operator equation. We can write in the number. That means when we use the eigenstates of the Hamiltonian, we have this matrix equation. We see there is still a self-consistent equation for the matrix elements of the transition matrix for any energy. And then we see the multiple scatterings now. That means because if we do it perturbatively iteratively, then the potential there appears several times or multiple times, and we have the multiple scattering. And we see the multiple scattering, even quantum mechanics leads to, as I mentioned, dynamical renormalization of the bare potential. This was the static scattering theory, but we will need the dynamical scattering theory, and for the description of dynamical scattering, we will need to introduce green function. Also, you heard yesterday. Then again, we split the full Hamilton in the bare part, and we saw the bare green function. Now it is a boundary condition of the integral equation. This again is well defined if we do the Fourier transform to frequencies or to energies, and these energies away from the real axis is well defined. It's the bare resolvent, and the full propagator is defined this way. Now the potential can be dynamic. We will see in the many-body physics we will need the dynamics of the scattering potential, because the scattering will be not external, but will be due to the presence of other particles. And now we can write this Lippmann-Schwinger equation, or also can be Dyson equation in this way, as Huber yesterday mentioned, and it is written in the full the time-dependent potential, which is now written in this Dirac picture. That means this external time dependence is added, but is extended by the propagation by this bare Hamilton H0, which I turn back in this many-body system. That means this also can be written as a kind of Lippmann-Schwinger equation or Dyson equation, where we see again this is a full propagator, this is a bare propagator, and now we see there's a full propagator with this potential. What is now important in quantum mechanics, always this, in this part, which is it is also self-consistent equation, but it's a linear equation in the full propagator, but here is still the propagator which is actually known. We will see in the many-body physics that this kind of equation can never be constructed, and here this part is usually replaced by self-energies unknown and should be defined from the perturbation theory. So far about the connection to the problem connected with quantum mechanics. Now, if we go to many-body physics, that means not three or few body physics or few particles, we go really to many-body statistical systems. And the basic difference between the quantum mechanics when we have a single individual particles is that we have the indistinguishability of equivalent of the same particles. That means we must include exchange interaction. That means we cannot follow the individual particles, and we should describe the system, the whole system, as a coherent state, like a fluid, either gas or liquid, and this should be described as a whole. We have still the problem as we had in quantum mechanics. That means we had in quantum mechanics the positive energy, which is the energy from the spectrum of the Baire Hamiltonian. We had this scattering state in the full solution. This will correspond in this many-body physics to normal thermodynamic phases. The bound states, which are the different, which is energies which are below the spectrum of the Baire Hamiltonian, then will correspond in many-body physics to order thermodynamic phases. And then we see that in this problem, in many-body physics, thermodynamics, which describes actually, which is the effort to resolve the background, the ground state or equilibrium state, is tightly coupled with dynamics due to non-trivial quantum eddy vacuum, which should be solved with other thermodynamic approach. But still, we can see, even though we have a coherent state, that I mentioned as the basic element of not elementary particles, but states, but scattering events can be introduced. That is the final, although this ingenious invention by Feynman, who simply replaced the Schrödinger equation, non-local description of quantum mechanics, with local particles of space-time picture and Feynman trajectories, Feynman integral, and then introduce Feynman diagrams, which will be used and can be used to interpret the physical, the effects which take place in the many-body physics. However, we pay the price because before in quantum mechanics we have one particle which is scattered on the well-defined Hamiltonian or well-defined potential. Now we have something which have a real and virtual scattering. The real will be real asymptotic stage which come into interaction with the other. We have the outgoing particles, and then in between have the real and virtual scattering, which we shall take care of. We never know if the particle which coming into interaction it goes out, but it doesn't matter. But it's still there is some conservation of charge. We will see that help us understand or help interpret the phenomena as interaction or the scattering event. So how do we describe quantum many-body system? We should go from the Hilbert space of one particle Hilbert space to Fock space, because we have to introduce the indistinguishability of particles, and this leads us to two statistics, Bose and Fermi statistics. It depends what so to say the symmetry the wave function have. The basis of the full Fock space is simply products of anti-symmetrized or symmetrized products of eigenstates of the one particle Hamiltonian. That means still the basis of the spectrum of the one particle Hamiltonian from quantum mechanics is the important, to say, the decisive for creation of the many-body representation. We replace the wave functions here with creation and annihilation operators, which actually is a kind of the second, what's called second quantization. Where from wave functions, from vectors, we go to operators, and these operators obey the canonical commutation or anti-commutation relations as follows, whether we have the fermion, bosons or fermions. And then, of course, we have we create the representation space with the Baire Hamiltonian, with all the eigenstates, and we suppose the interaction which we introduced does not change the Hilbert space, which is constructed from this basis of the products of basis of the Baire or the unperturbed Hamiltonian. And of course, the particle interaction we will see, because this general particle interaction will not commute with the Baire Hamiltonian, with the unperturbed Hamiltonian. We have to introduce dynamical scattering potential, we will see, and we will be very close to the dynamical Lippmann-Schwinger equation for green function in quantum mechanics. Okay, now, how do we introduce interaction? As I mentioned, we introduce creation and annihilation operators. Here we have this psi can be the arbitrary one particle states, which is the creation with this dagger means as creation of the operators, and this dagger means also Hermitian conjugation between these two. Alpha, beta, these are the indices of the maybe eigenstate, but it need not be diagonal in this Hamiltonian. It is one particle part, the quadratic part we see of the Hamiltonian, and then we have the real interaction. And the interaction in the low energy physics and condensed matter usually is a non-relativistic Coulomb repulsion, and we see the Coulomb repulsion is simply this Coulomb interaction, that means proportional to the square of the charge of the present electrons or particles. Mostly we will deal with electrons. The other one particle stays. Again, we see we however have these four operators, two couples of pairs of creation annihilation operators, and we see is a quadratic part, is a quartic part, and actually when we look at these operators in the Fock space of this many-body state, these two parts of Hamilton do not commute. If the operators do not commute, they create quantum fluctuations, and these are quantum fluctuations due to the presence of particle interaction. We have no external potential. We have this is homogeneous, and we can diagonalize it. However, if we want to describe the thermodynamics, I mentioned we have the several scales in the many bodies. Yesterday, the speaker spoke mostly about the really local scattering, microscopic distances. However, as I mentioned, if we want to describe many-body physics, we should first to resolve the equilibrium state, thermodynamic equilibrium state, and this is dominated by long-range fluctuations. That means we should really look at the long distances and somehow suppress the microscopic, so the Schrödinger equation of the microscopic scale, or the microscopic length scales. So we go to so-called tight binding description. That means we separate the whole lattice, the whole space into elementary cells, and don't forget the interaction within the elementary cells. And so we get this description is I will also speak mostly in my theoretical part of the single orbital Hubbard model. That means we have these discrete states which are described as a kinetic energy, which now is a momenta, and the momenta from the first Brownian zone, and this we replace this interaction, which is it depends on the distance. We neglect the distant short distancing and replace this interaction. This is spatially this long-range interaction with a short one, which is the average interaction within the one elementary cell. And the only interaction, because they have a single orbital, the only electrons can appear if they should have different states because they are fermions. This is the only possible interaction we can have. This is really a paragon model for interaction to describe most of the thermodynamic effects. And if we want to resolve the thermodynamics of the many-body systems, we usually start with the Hubbard model. And once we have this, when we resolve the long-range fluctuation, we go to the short-range scale, and we go to the density function with other combinations or other methods to describe the Schrödinger equation of the behavior of the system within the elementary cells and how to match the elementary cells. This other problem you will hear during this course. If you really want to separate, because you have this K-dependent full lattice extended model, if you want to really study, quantum fluctuation, pure quantum fluctuation, we can neglect spatial fluctuation and concentrate on the dynamical ones. That means the non-commutativity of these two parts of the Hamiltonian. And then is another canonical model, or the paragon model, is a single impurity Anderson model, where the conduction electrons are hybridized with single impurity, which is hybridization term, and the Hubbard interaction term, is on this impurity. The advantage of this model is we have the exact solution for this, so it's so to say also a model on which we can test the validity of the methods we use, because the exact solution for neither of these models exists. So we have to introduce perturbation. Reliability of this perturbation methods means we should have the mean, or have the limit at which we can control how reliable these approximations are. Actually, the most interesting part is here in this model is how we can go from weak coupling, where this U is small, we can go to strong coupling, and usually strong coupling leads to changes of the thermodynamic background, thermodynamic phases, which will emerge at low temperatures. Okay, now what we have to do, as I mentioned, we should first solve the thermodynamics before we go to the dynamics and follow the spectral properties of the system. The thermodynamics is governed by thermodynamic potential. It's a grand potential in this case because it's a Fock space. The particles are not concerned with fluctuation. Particles are governed by the chemical potential, and this grand potential is a function of Baire-Hamilton interaction, Hamilton, and external perturbation. Why do we introduce external perturbation? Is something like the external potential, but it's a many-body external perturbation, which is introduced to check the linear response theory and to check whether the paramagnetic or the disordered phase or high temperature phase is still stable at low temperature. And since we have in quantum physics, the external perturbation can be very, very weird or rather weird. We have to introduce the external perturbation is a generalization of the density interaction with the potential or the external potential. However, the external potential need not be real; it can be quantum because still, and then of course the quantum of this imaginary part cannot be measured, but still it can be used as auxiliary means to test stability of the system with respect to fluctuation, unexplained. First, the first interaction which I call eta parallel, which is simply the creation of the particle with spin sigma at the coordinate 1, is this space-time coordinate, and annihilated is in the point 2. This interaction, this field is real, and this interaction conserves charge and spin. However, we can introduce complex fields, eta, which creates electron with spin up, annihilates the electron with spin down. That means this is a spin flip process, and this interaction does not conserve spin, but conserves charge. Here, actually, as a psi field, we have creation. We have annihilate two electrons with spin up and spin down. That means we conserve spin, but we do not conserve charge. And this interaction is actually responsible for superconductivity. And the other one is does not conserve neither spin nor charge. And to return to the physical interpretation of this interaction or this external perturbations, this field is responsible for longitudinal magnetic order. This is a transversal magnetic order. This is the singlet superconductivity, and this is a triplet superconductivity. That means essentially we need to introduce them to really test the low temperature behavior of the full thermodynamic system. Like, as I mentioned, this is analog of the searching for bound states in quantum mechanics. This is many-body physics. And what we shall do, that means we split the Hamilton into the Baire and the quadratic part, which you can exactly solve, which actually is a set of harmonic oscillators, which is a dispersion relation, is a first Brownian zone, is a spin, is a magnetic field, and there's a chemical potential which reduces to Fermi energy at zero temperature. Then we add the time dependence to the propagators, but almost imaginary time, because the temperature is also a continuation to the time to imaginary axis. So we have this propagation which is not unitary, and that means we see that this relation does not hold, and actually this relation holds on the left to right, okay? But still it is an analog of the perturbation theory of the zero temperature many-body physics. Now, to describe the interaction, we have to introduce green function, but now we have the Fock space, and we have different types of green function. And the general green function is actually as a product of the product we see of the product of annihilation and creation operators of different coordinates. These are, so to say, external vertices that should be the particles from the Fock space with the energy of the unperturbed Hamiltonian. These are associated with called scattering states. And now here is everything here, which again is propagated with this Hamiltonian H0, is the interaction part in the Dirac picture, and this describes the thermodynamics, the background in which the particles behave or move. And the trace zero means they have this trace over the Fock space of this Baire unperturbed Hamiltonian, which is exactly known that we can do that, and that is the full partition function from here. Of course, the green functions are non-trivial because we have several times, but we will not need all of them. Actually, what we do before we analyze the green function, we should introduce the perturbation theory, how we really how we reach the results with this interaction. The unperturbed green function can be diagonalized in Matsubara frequencies. That means there is a dispersion relation in the Fourier space. That means we have a Brillouin zone. This is a constant. And then, of course, the time propagation, imaginary time propagation is in the Fourier transform, is the Fourier series, is the Matsubara frequencies, which are odd frequencies for fermions and even frequencies for the bosons. But we describe many-body electron or many-body fermion systems. Of course, this is well defined, that means diagonal, and then we can write the full thermodynamics is described as a partition sum or grand potential is a logarithm of it. And we have the C, we can write instead of T product, which is the standard representation in many-body physics with the time ordering, which also is part of the definition of the green function. Now we can write as a functional integral, however, with Grassmannian variables, which are anti-commuting variables. The quadratic part, which can be solved exactly, is the inverse bare green function here, which is diagonal in momentum, frequency, and spin as well. And then we have the interaction part with the quartic, that means these are densities, these are products of creation and annihilation of process, quartic part. And we see this part of Hamilton is diagonal in time and in space. And then you see that these two parts do not commute, and that's the only way to deal with such a complicated problem, even though we have this functional integral which can be defined on a perturbative, is that to expand the quadratic part. The only way to reach any quantitative results is to introduce perturbation theory. So the perturbation theory now allows us this is the tools how we match the physical behavior, the behavior of the many-body system with scattering, what we know with scattering. And then, for which, as I mentioned, we introduce Feynman diagram, because it's the easiest way to control, interpret, and have a fine physical interpretation of the events which happen there using Feynman diagram. That means we introduce a solid line with oriented solid line from one coordinate to one is the space-time coordinate. Then times go from left to right. The arrow indicates propagation of charge. That means it should be particle if the time is smaller here and then it's bigger. That means first is created, then it's annihilated, the solid line. The whole propagator will be inverse in time. That means it goes from right to left. That means from higher times to lower times. And then we have this bare interaction. And that bare interaction is not caused by external potential, but actually the presence of other particles. Okay, that means one particle goes here. That means that emits a photon, which is absorbed by other particle, and then the exchange of photon is just the photon, and the Coulomb repulsion is infinite speed of light. That means it's horizontal. Just it's an instantaneous interaction, and they change their behavior in momenta also and also in energies. And now we can come to the scattering processes, which we have. We have the two types of scatterings. It's a one particle and two particle scattering. Of course, we could have more particle scatterings, but we will never use them. The one particle scattering is as follows. We have to say, we can see this should be our external state. That means we just connected to the external vectors of the green function. Now it emits photon. It exchanges. Now it is a bubble. You see, there is no external lines. That it interacts with the electron with a quantum vacuum. Quantum equilibrium states is composed of electron-hole pairs. It can be excited. Now electron-hole virtually exists and go, then exist for some time, and we are annihilated back. The electron is absorbed back, and the electron propagates. That means if you follow this particle, this is typical one particle scattering, and this is kind of dynamical interaction, which the dynamical scattering of the one particle function. Okay, we have also two particles, which is real. To say we can take two real asymptotic states. If we follow them, we have the one particle emits a photon, absorbs a photon. Now we have this in the form of electron-hole scattering. That means there is this kind of hole and there is electron. This is also convenient to write. I am used to use the electron hole description, but we know that in this electron hole symmetry, we can describe either with electron as holes, and we know this Dirac pictures of Fermi C or Dirac C, that it's if the ground state is filled with electrons, it's better to see holes in the C as elementary excitation, because at the end we will be able to describe only elementary or a few excitation above the ground states. So now, as I mentioned, we have many green functions, n particle green function at the end, but we will not use all of them. What we will definitely have to use or have to take into account are the two types of green function, one particle and two particle, which we define explicitly. First, we introduce a density matrix, which contains all the thermodynamics, all the background information on which environment the particle move. Now we have the one particle green function, which is a time ordering of these two operators at space-time, again with different with spin sigma 1, R1 bar, and T1 and T bar. And this is actually a full green function, and this is the full thermodynamics. If it is one, which could be, for instance, in this approach, there is no interaction, that means it will be trivial, so to say, green function of the system. And then to the one particle, we introduce the two particle, which actually is the product of four. It's a four operates against the density matrix. It's the same. We have the four external coordinates. And now we will need to find approximations how to calculate the one particle green function with this density matrix operator and the two particle green function, which are actually coupled due to the equations of motion. And then this is actually very unique for the many-body system. The many-body systems are those systems in which the particles do interact. And then we see we saw in the Fock space, then the interaction will contain four creation and annihilation operators, two pairs of creation and annihilation operators. And that means it changes because you know the Fock space is a sum of this one particle, two particles, three particles, all n particle states. And that means the interaction changes the Hilbert space from one particle to two particle, from two particle to three particle, and so on. So this is a problem that once we want to calculate one particle green function, which we really are interested on single particles, elements in which we measure one particle, one single, so the input part or the incoming particle and outgoing particle, then we have the band propagation, there is interaction. And now you see that this equation, the so-called Schwinger equation, here is this potential. Now, however, here this is not the same one particle green function, but here is a two particle green function. That means the red is indicated the function which is unknown. If you want to resolve this function with these interactions, so everything is dynamical, we should know the two particle function. If we construct the equation for the two particle, we would go to three particle and so on. That means the methods of equation of motions, if we cut off this chain of hierarchical equation at some level. What we prefer using Feynman diagram, different scheme. We should formally close the equation for the one particle green function within the one particle space. Here it is the same, and now the interaction here, we have this one particle function on the right hand side. However, here we replace these two terms, the known and unknown, with one unknown, which is called self-energy, and this is the Dyson equation. The Dyson equation actually tries to cut or to reduce the equation of motion for the one particle within the one particle Hilbert space as a subspace of the full Fock space. Now, if you look at the two particle functions, and the two particle function generally contains a bare uncorrelated propagation, which we can subtract from it, and then we can subtract also one particle incoming and outgoing particles, and we introduce a two particle vertex. There also is unknown. So if we want to describe this one, we should know this function, which is also unknown. And now, if we combine these two equations to Schwinger equation, we get the fundamental Schwinger-Dyson equation, in which two particle vertex gamma and self-energy sigma are coupled in a single equation. I will come back later to this, but it's very important to that. The effort of many-body physics is now to determine this function sigma or this two-particle vertex gamma. It depends which method we use. And now you see, this is something like, okay, similar to Schwinger-Dyson equation. Here the scatter is completely dynamical, and the scatter should be described or should be determined by perturbation theory by the knowledge of the thermodynamic background, the environment in which the particle move. So we have now, as I mentioned, dynamical scatterings, and we will try to somehow simplify the description as much as possible. And because, as I mentioned, we need to deal with one particle and two particle functions simultaneously, and in the effort to describe maximally precisely the effect of interaction on the movement of single particles, also two particles, because the two particle functions are responsible for many physical quantities such as susceptibilities, response function, and so on. And they are also responsible for checking the linear response theory, whether we have a new low temperature phase or not. So physically, one particle and two particle functions are important and necessary to be known. So to describe multiple scatterings or the effect, how do we construct the dynamical scatter? We introduce irreducibility in the green functions. And the irreducible function generally calls vertices. We have, again, several types of irreducibilities, and we restrict on one particle and two particles. And then again, we use Feynman diagrams, and we know the one particle reducibility is such a Feynman diagram representing some process which cutting one particle line split into two separate parts. Irreducible means it doesn't happen. One particle irreducible function, green function, is actually self-energy. One particle irreducible two particle green function is two particle vertical. That means now, knowing the sigma and gamma, we can construct all the two particle and one particle function completely. That means we restrict our perturbations here to determine sigma and gamma. Then, however, we introduce two particle self-consistency. That means we know the self-energy determines the one particle green function via Dyson equation. Now we will be also eager how we can define this the two particle vertex with something which could be called a two particle self-energy, which actually are two particle irreducible vertices. However, that means we introduce two particle irreducibility, and that means if cutting two particle lines, this solid lines, split the diagrams into two separate parts. That means when it's irreducible. Irreducible, it doesn't happen. However, now it appears that we have a simultaneous propagation of two quasi-particles, either two particles or as electron and hole. And now we have actually several types of, because they are mathematically different or irreducible representations of full vertex gamma, and we introduce different irreducible two particle vertices which we denote lambda. Alpha is a channel in which we have. We have strictly electron hole irreducibility, which we have two asymptotic states, which electron and hole, which are anti-parallel lines, which propagate simultaneously, and the irreducible part we will call lambda electron hole. The same electron hole, which we have the parallel lines, that mean left to right or right to left, this particle hole. Also, we have electron hole irreducible. However, when we cut virtual states, virtual pairs, as I mentioned, as I showed in the one particle scatter, we have this bubble which is generated from vacuum, and this cutting is a different irreducibility in the two particle. Okay, it may seem weird that we have, so to say, made the system more complex than it before, but we will use this ambiguity in the two particle irreducibility to our convenience, as I mentioned later. Okay, now to construct the Dyson analogs, or the equation, or analogs of Dyson equation for two particle vertex, we now separate the vertices into two parts, the direct and transpose vertices. you must imagine then the particle line, the particles, charge and spin are constant, even in the black box where the interaction takes place. That when one particle comes in, it should continuously go through. And we have the one particle coming in and two particles goes out. So either the particle goes somewhere here, scatters, and then goes out, and we call it direct because the other should go this way, or it goes the other approach. It goes here in the upper left and goes up or down, down below. Okay, these are transfers. Here we have this, because we have conserved the full energy and momentum is conserved. We have three independent variables over the three edges here. And the K is a 4-vector notation, the 3-vector and Matsubara frequency. These are for bosons, these are even, they are odd. And I mentioned this concept. If the spin are the same, the spin are individuals are independent, they are the same, we have the symmetry relations due to the fermionic structure of this vertex. And now we can construct, in defining this, we can construct the analogs of Dyson equation for the two-particle vectors. How can it be constructed via irreducible vertices? And then we have this so-called equations that are called beta-salpeter equations, and we have, because of three irreducibilities in this system, we have three types of beta-salpeter equations. And now again, everything is done in Feynman diagrams because it's easiest way. It's really, it's saved a lot of work to writing indices and so on. Only one have to take into account all the conservation should be obeyed. Now we have the vertex, which is independent of this channel because it's called the channel. And now we see this is electron irreducible because if we cut these two lines here, this diagram split into two. That means this reducible diagram in this electron hole channel, this is irreducible. And we see the full vertex always the sum of irreducible plus reducible. The minus sign here is because of the Fermi structure of the system. Now, and again, you should follow it. This one is a direct propagation. The electron goes here, scatters, and goes out here. This is a direct, because this is a direct vertex. Now, here's electron scattering. That means now this propagation is, okay, it's parallel. That means we have to interchange these two lines below. And you see electron irreducible, but here is again, here we cut these two lines because these are not connected, they are only indicating in which direction it goes, because we use the electron hole direct representation. Then we're cutting these two lines is reduced. However, this is a new diagram because we can see this transverse, that means it goes this way, this way, this way, and this way, and that means these spins are interchanged here, but still contributes to the full vertex gamma. But the third vertex is the most complex, and this is just the cutting the virtual states. We have this full, again, the same vertex gamma, this is irreducible, and now we cut not the horizontal propagation but the vertical one, and then we have still the direct propagation from here to here. Here it is again, here it goes this way, that means these spins are independent, and we sum over this one and the full vertex. Now, however, we can combine the transverse and the full, and again full and transverse, direct and transverse. There's more. Again, the signs correspond to the take care of the anti-commuting form of the structure of the particles. So we have the three types of the irreducible or the representation of the full vertex. That means the whole perturbation, the whole description reduces to find sigma and to find lambda in the one of these three channels from which we can use a beta-salpeter equation to determine two-particle vertex and Dyson equation to determine the one particle. And now we come the fundamental object is the multiple scattering. What do we understand under multiple scattering in many-body system? Actually, the multiple scattering is now understood as a renormalization of the irreducible function. The irreducible function are now this sigma and lambdas, and now we see if we start the perturbation theory, we have this something that the sigma and lambdas are functionals or function of the bare propagation and the interaction. Now the one particle self-consistency means that we replace this function with a new function, which is now depends only on the full green function, which contains the sigma itself, like a self-consistent description, but still bare interaction. The same it holds for the two-particle irreducible vertices. Now we can go further. We can introduce two-particle self-consistency. That means we can replace both. We can replace the bare propagator with a full propagator and the bare interaction with a full interaction. That means the irreducible parts, which is now the dynamical scattering. And actually, if you can see this something similar what you know so for quantum field theory, that the quantum field theory to get the result we have to renormalize charge, again mass and charge. The one particle self-consistency is actually corresponds to mass renormalization, while the renormalization of the vertex corresponds to charge, because we know the interaction is proportional to the square of the charge. And now, of course, the full one particle propagators in this G would be the full containing cell energy sigma. Now, but the problem is we can stop here at this level, which seems to be easier and of course easier to reach. However, we can show that one particle self-consistency is not enough to control the critical behavior. That means we can see that we can have a spurious transition, and also it's shown in the Anderson model that the strong coupling is not well reproduced if the two-particle self-consistency is not taken into account. So, first thing is, how do we actually introduce a one-particle self-consistency, which is actually the canonical Bain-Kadanoff approach introduced in the 60s, last century. So it means we replace the generating function of the perturbations, we build the thermodynamic potential, which now is a function of full G and sigma. Generally, the sigma and G are complex functions depending on spin, momentum of the first Brian zone in this one band Hubbard model and one orbital Hubbard model, and Matsubara frequencies. The same here. Only analytic properties should be obeyed as are different. And then we introduce a new, let us say, Latinger-Ward function, which is function of G and Berry. Now, that means this is a variational function where sigma and G are complex function, and the equilibrium values of these sigma and G are obtained from stationarity condition. The stationary condition are not a differential equation, but the first variational differential equation, and then it means this d omega over dg is 0. Then we obtain the equation for the self energy, and the d omega over d sigma is 0. We obtain the Dyson equation. And then, of course, here in this approach, this functional should be determined from the perturbation theory or whatever, and we know if we know this function, we know everything. And we see that the importance of Latinger-Ward function is here, that they actually, if we know this functional dependence of G, we can use functional derivatives to derive irreducible vertices. And that means the first derivative is the self energy, second derivative of this is actually the vertex quantum. Of course, here we have the three variables, and then of course, if you go into the perturbation, we should go out of equilibrium. That means sigma is no longer proportional only to one variable as equilibrium, but also two. And the combination of the three different ways we can do that defines a different irreducible function. Important thing is to know, to mention that this G should be the full G containing self energy. That means the self energy from the Dyson equation. Okay, everything is fine. The only problem is how do we define the function of phi? That before we go, as I mentioned, there is the importance of the connection between one and two particle functions. And the one and two particle function, as I mentioned, one connection is the definition of the self energy which we obtain from this equation. However, this is the equation of motion. However, we also have a conservation law, which are expressed in the Ward identity. We actually have two again. We have the mass conservation, which is due to continuity equation, which can be written in the integral form in such a way that the difference of the self energy is related with the irreducible vertex in this electron hole channel and the difference of the green function. If this microscopically obeyed, the macroscopic continuity equation or macroscopic conservation is obeyed. However, we have another conservation, and what we call the particle interaction conservation or charge conservation. That means all interactions comes only for charges which are from the present electron. And we know the charge is carried by the electron, and electron is a mass. That means we cannot we cannot separate charge and mass of the electron. And if we do simple this derivative, it takes a function of this, the generating or the thermal potential. We derive this is a partial derivative with respect to u, and we introduce a local chemical potential spin dependent and do the second derivative this time. These two derivatives should be the same. Now we see this depends only on the charge because u is proportional charge. And here it depends because chemical potential plays a role of mass. So we see that this derivative should be equal to the difference of the temperature, difference between local compressibility minus local susceptibility plus this product. There's also some rule which should be obeyed, which guarantees that all the interaction is generated only by the present electrons in the system. But it's very difficult to comply with. Simply, as I mentioned, first connection between one and two particle function is a Schwinger-Dyson equation, which I did not mention, but this is simply the mathematical form that we have the full vertex here and there's one particle propagators. However, it's too complicated. This is the density of the spin density, charge density, the spin density. The spin is plus minus for spin up and down. However, it's much easier to represent it diagrammatically in Feynman diagram. Is a self-energy, is a Hartree term, and is a contribution for vertex. But we see the vertex only a dynamical contribution to the self-energy. There's one connection between sigma and gamma. And the another connection is the word identity I mentioned, is a conservation of mass. And the difference of self-energy is this lambda connected with delta G. However, in the full theory, lambda using beta-salpeter equation determines the gamma. But the beta-salpeter equations are not part of the Behm-Kadanoff approach. That means it's never guaranteed that this gamma obtained from Schwinger-Dyson equation, which is obtained from the Behm-Kadanoff approach, is such that this vertex is the same as the vertex in the beta-salpeter equation generating this gamma. So that means, what does that mean? That means word identity imposes a restriction on 2p vertex in the Schwinger-Dyson equation. That means it's very difficult to obey. If we can get gauge transformation to see a two-particle function of left-hand side, which is Schwinger-Dyson equation for the self-energy. This is the word identity using beta-salpeter equation to two-particle response function. These two functions should be the same if the charge, the whole charge, is carried by the present electron. However, the problem is that no approximate theory can comply with this restriction. The only solution we have either have the single self-energy as two vertices or vice versa. What happens? That means the Behm-Kadanoff, because of generating function of sigma, has from the definition single self-energy, but it has two vertices. But it may be a problem because the two particle vertex determines criticality and critical behavior, which is measurable and should be uniquely defined. And an example, I show you how the Reynolds measuring scheme works in the Hartree approximation. This is again this Behm-Kadanoff grand potential, which is the non-interacting part of the self-energy green function, sum over these frequencies, momentum spins, and now there's a Latinger word function, which is a simple product of densities. Okay. Then the self-energy from the stationarity. So this way, is simply Hartree self-energy. The spin sigma bar is minus spin. Then the Dyson equation also works well. And now irreducible vertex. That we use the second derivative of this function. We obtain this lambda is u. And now if we use a beta-salpeter equation, which goes beyond the Behm-Kadanoff approach, we obtain the two-particle vertex from Schwinger-Dyson, from beta-salpeter equation, and it's irreducible vertex. But it's not. However, if we do that, this phi is a two-particle bubbling. However, Schwinger-Dyson equation, which actually is the same as the equation of stationarity of omega, it defines it this way. That means there is no vertex there. That means the two-particle vertex from Schwinger-Dyson equation is zero, actually zero. And we see in this way that the vertex contained from word identity and beta-salpeter equation is non-trivial. determines non-trivial dynamics, thermodynamics, but the two-particle vertex from Schwinger and Dyson equation is 0. We see that these two vertices do not. But this is the same situation for any approximation you use. You can never have, you can never combine with this vertex constructed from Schwinger, Dyson, and the vertex constructed from Ward and Bethe-Salpeter. However, if we want to describe quantum or criticality, generally quantum criticality, we need a unique two-particle vertex to have a unique critical behavior. And then it can be resolved by the two-particle approach. And now this is the last part of my talk. I will discuss the alternative way how to describe the many-body physics with starting from two-particle vertices. That means we replace the generating function, which was the full grand potential, with a two-particle irreducible vertex, which should be determined from some approximation, perturbations or whatever. And now we take as a generating function for the approximation we have. This is uniquely defined. We have the Bethe-Salpeter equation, vertex, and so on. And since we want to describe quantum criticality, that means we pick up the Bethe-Salpeter equation for the gamma, which is singular in the critical point. However, the gamma is critical, singular, this is regular, and then we take the external perturbation, which we use the external field with respect to which the fluctuation destroys the linear response theory, which we use. That means to determine the order parameter, because the order parameter is the Legendre conjugate to this external field. So we now, the one-particle function, we split into odd and even function with respect to this field. That means we take the odd symmetry, that means plus eta and minus eta, with the difference between these two. It contains only the odd powers of this potential eta, and this is a symmetric part which is even power. Since the critical behavior is, so to say, the critical becomes only at 0, this field is 0, so we will try to reproduce only qualitatively on the leading order contribution to this external field. And then for this reason, to describe correctly the quantum criticality, the two-particle functions are not necessary to split into even and odd. Only even functions are important because they are non-critical, the irreducible part. So now we split the self-energy according to this, and we take the role of these two self-energy. We take the odd self-energy with the odd symmetry, and we determine it from the linearized form of the Ward identity in respect to sphere eta. This is a symmetric function with eta, is antisymmetric. That means really it's a linear power in H. It means linearized, it's resolved exactly in the linear power of eta, it's a Ward identity. And then we take this even self-energy, which does not contribute to the order parameter, or only, so to say, in the leading order. So we can use the Schwinger-Dyson equation for the odd part. This is a Hartree term, which is also spin independent. It's the full charge density, and this is the dynamical part from the vertex. And now, knowing the eta vertex symmetric part, we can use Bethe-Salpeter equation to determine gamma, and we take the Schwinger-Dyson, this density, the self-energy. That means what we did, because we have a single vertex, we need to have two self-energies, but we split them into two. This is an order parameter which is non-zero only at the low temperature phase, but is a full self-energy symmetric, which does not decides about the critical behavior, but is defined everywhere, and this is determined by the Schwinger-Dyson equation. If we had the exact solution, the two functions two definitions should be the same, but in approximate theory, it is not the case. So now, the last thing is that why do we really care about two-particle functions and then two-particle self-consistency? As I mentioned, the one-particle self-consistency is not enough to handle the critical behavior, because we can have a spurious behavior on the incorrect the strong coupling limits. So we now introduce two-particle self-consistency atop of the one particle one, and to suppress the spurious critical behavior and to obtain the correct limit and strong coupling. Then we take the two channel. That means okay. We take two channels. One channel is a critical channel in the magnetic interacting systems. Is the electron-hole scattering channel, and we should take one screening channel. The screening channel somehow decrease the speed with which the system goes towards the critical point. We take these two channels and mix them together in the so-called Parquet equation. The Parquet equation, based on that the full vertex is always can be written in the sum of the irreducible plus reducible in any channel, but the reducible channel in one channel becomes irreducible in the other channels. That means you have this equation, and this I is completely irreducible to two-particle irreducible vertex. That means if we know this one, we can calculate this case from this beta-salpeter equation, from this Parquet equation. And now if we take the two-particle channel, the two-channel Parquet equation, we have the two equations for this reducible and irreducible. However, if we replace this fully irreducible with this bare interaction, which is kind of Hartree approximation at the two-particle level, so we have this one, that these blue terms cause that and we try to resolve the full set of these two-channel Parquet equation, it completely destroys the critical behavior. Although we know, for instance, the single impurity Anderson model, there is a critical behavior, so it must exist. We have either two choices. Either we replace this U by more complex functions, or we try to somehow reduce the particle Parquet equation in such a way that we reproduce the critical behavior from weak coupling and then continue it correctly to the strong coupling. So it is done by the so-to-so reduced Parquet equation that we suppress these blue terms, which destroys the criticality, and in the hope that the higher order terms should compensate for those. And then we introduce the reduced Parquet equation, and these are the similar that is the full beta-salpeter equation for the reducible, but the irreducible was corrected to remove there is no self-correction in the anomalous or in the reducible function. Again, these variables are integration variables. So it's a still integral equation, very complicated to solve. So what we do the mean field approximation, and the mean field approximation we simply replace the lambda, which is non-critical, it's a constant. We simply suppress the finite fluctuation with respect to long-range fluctuation, which can be divergent. And then it is a constant. You have a full solution for the reducible vertex. However, if we take the reducible vertex into the equation for lambda, then we obtain in this equation on this part is frequency dependent, is frequency independent. So to reconcile this part, so we should neglect the point-wise the validity of the equation by introduce some kind of averaging which is not unique, but still it does not change the criticality. It does not change universal behavior, but it changes non-universal behavior. And there was special in this some averaging. We can end up with such kind of equation. We see this nonlinear equation from lambda. Here are the charge density, spin densities, and here is the screening integral, which I explained. There's a particle density, magnetization or spin density. Here is a screening integral. Here this denominator is very important because this is the function which can go through zero at the critical point. That means that zero frequency static phase transition and some specific Q which determines the order or the type of the ordering. And then because of this nonlinear equation, this critical point can be reached only if the singularity, because it's the integral of the frequency of the momenta here, it's and frequency as well, I forgot this. So it must be integrable, that only integrable singularities can exist. And this is the way that two particles self-consistently, which suppresses spurious phase transition. And now, what I have this interest the electron hole bubble and also electron bubble, which came into place due to this averaging that I used to determine the single equation for this sort of effective interaction lambda. Okay, and then is the major, the consequence or the most important consequence that this only integrable singularities are allowed due to self-consistent screening of the interaction. That means really two-particle renormalization, two-particle self-consistency. Now, the Parquet equations are equations for two-particle vertex. However, we will also need the one-particle function, so we should go back from two-particle vertex to one-particle function. The one-particle function is simply defined either this is what we call thermodynamic propagator, which is static renormalized. However, this odd part, the even part is only Hartree term. However, the odd part, which is responsible for the magnetic order, now in the magnetic system, is with the renormalized interaction. This is the stage. Otherwise, this propagator replaces a Bell propagator in the standard perturbation theory, which you call thermodynamic propagator because it reproduces thermodynamic properties, the order of the long-range order. However, we also have this dynamical part, contribution to self-energy, which is given by the Schwinger-Dyson equation, which is given this normal, even part of the self-energy is frequency dependent. And of course, the Schwinger-Dyson equation is also given here. That means the odd self-energy is given in this way. This is the Hartree term, and this is the even self-energy from the Schwinger-Dyson equation. And now, of course, if you want to have the correct description, that here is a full green function which containing the self-energy here, and it can be either thermodynamic one with these propagators or these propagators if we want to have this fully one and two particle self-consistency. However, it appears that not always it's convenient to introduce full self-consistency one particle also here, because the Kondo behavior is more difficult to reproduce than in this if we do it in this way. And this actually is the end of the story. And then, of course, once we have the full self-energy, we can go the same as we did before. That means we can define the physical quantities, which are all defined from the full self-energy, the odd part and the even part, Schwinger, Dyson, and Ward. And then we have the full particle density, spin density, two-particle bubble if we need it, what we used in the Schwinger-Dyson equation. And that's okay, what we have, and all the physics is defined. Susceptibility is also defined from the two-particle function, which can be either derived by the derivative with respect to magnetic field or other definition. And this the two-particle approach in this way guarantees the consistency between one particle and two-particle function, at least at the quantitative level. So to conclude, the particle scatterings in many body systems, so the spectrum of the full Hamiltonian unknown, we should introduce perturbation theory, fundamental objects are asymptotic states, these are quasi-particles, and interaction can be treated only perturbatively, and is the source of the scatterings of these quasi-particles. Green function describes the propagation of the quasi-particles, which are renormalized by the single particle scattering, which scatter on the excitation of the thermodynamic background as the virtual pairs, and the one particle irreducibility introduces self-energy as an effective dynamical scattering for the one particle propagation in the thermodynamic many-body surrounding. In two particle scattering, we can take two asymptotic states, and where in mutual photon exchange, we introduce two-particle irreducibility and Bethe-Salpeter equation, which determines the full two-particle vertex and two-particle function. And this, as I mentioned, one particle self-consistency or renormalization is mass renormalization, and this is charge renormalization. And the multiple scatterings I also mentioned is the actual renormalization of irreducible vertices. This dynamical scatter is for both one and two particles scattering, two particle scattering processes. And then what we should remember is that we have an ambiguous way to relate one particle, two particle green functions, and these are the Schwinger-Dyson equation, which comes from the Schrödinger equation in the Fock space, and Ward identity, which represents the conservation of macroscopic conservation laws. And they connect single both connect self-energy and the two-particle vertex. And we have the two many-body approaches, the one-particle approach, which is the Baim-Kadanoff, which have a single self-energy but two-particle vertices. It is inconsistent in critical behavior. Its ordered phase does not match the disordered one. This approach can be used correctly above the critical point because there is no order parameter. However, if we had this ordering there, we have the low temperature new orders, new phases, then we should use two-particle approach because we should have only single two-particle vertex which determines the critical behavior. And then, since we have a two-particle vertex and we cannot comply with both Schwinger, Dyson, and Ward, we have two self-energies. But we split them into according to the fluctuation with respect to symmetry breaking field, the critical symmetry breaking field. And we have this old self-energy which plays a role of order parameter, which is connected with a two-particle vertex via Ward identity, and the even self-energy which is responsible for spectral properties and the spectral behavior, and it is defined from the Schwinger-Dyson equation. However, it is in the symmetric form with respect to the symmetry breaking field. Okay, this all and then defined. This is a further reading, and I would like also to mention that Java is my collaborator who is present there. Will present the application of this two-particle approach in his poster. Okay, thank you for your attention, and I am ready to answer your question if there are any.
He didn't hear the applause, so we have to repeat it. Now you have to repeat it. Okay, Vashe, can you hear us?
Yeah, I can hear you. Yeah.
So let's see if the questions you can hear. So, are there some questions? Hubert has one, so you can come here.
Towards the end, in the summary, you once more stressed that self-energy derived from the Ward identity and the Schwinger-Dyson equation do not agree in general. Does it indicate in any sense that one of the two approaches is superior to the other, or it just reflects that you use different approximation to get the result?
Can you repeat the question once more? Excuse me?
Oh,
yeah. So in your summary, you stressed once more, I think it's 3-4 slides above, you stressed once more that the self-energies that are obtained by the Ward identity and the Schwinger Dyson equation do not agree in general. Does it indicate in some sense that that one of the two is superior to the other? Now you are above already.
Okay, which? Okay, you can look at the Hartree approximation. Okay, which is typical, let's say, standard representation, which is Baim approach with the word functional. Then what I mean is in that way that if we use the Schwinger-Dyson equation in full, that means including all the fluctuation, the problem is if we go to the criticality. Because here, for instance, we see that if we have this sufficient strong interaction, this goes at the intermediate coupling to a critical. There is the Hartree or the transition to an ordered phase, magnetic phase. That means it's a critical two-particle vertex. However, the Schwinger-Dyson equation, this gives another vertex which is zero. It's trivial because it's zero, so we have nothing to compare. For instance, if you use a flex approximation, that means if you use a fully renormalized propagators here, then we have a non-trivial vertex here, lambda, which lambda is again u. However, this will be different. This will be also the same. However, the Schwinger-Dyson equation will contain another contribution due to the two-particle scattering. So it means we have two vertices, and the problem is if we decrease the temperature, this vertex goes to the critical point before this vertex goes. And if we come across the critical point in this part, on this side, so we have no way to continue beyond the transition. because to go beyond the transition, we should order the phase to guarantee the susceptibility stays positive. So to go there, this vertex, in the low temperature phase, this vertex is important. However, if you use only Schwinger Dyson equation, which is actually the way the Bames-Karanov proposes, so we can work completely well above critical point. However, below we are in the problem because we do not have we do not have the means how to introduce order parameter because the word identity is not valid. The order parameter should emerge at the same point where the two particle vertex diverges. And it is the case only when the word identity, at least in the linear, the linear as form what I introduced is obeyed. That is okay, so the meaning of this. Have I answered your question or?
Yes.
Yeah, thanks. Thanks, Vasek. Are there some other questions? Okay, if it's not the case, then thanks for joining us. We are also organizing always some kind of, if somebody has a particular questions to you, to your slides, the people will look on that. So we will try to organize during the school some Zoom meeting with you. So we will just send you email if some.
Sure. Okay, I will follow the program mostly in the morning. So if you do, you let me know any sort of questioning and answer. They might also the remote speakers will also be. We can organize, or you can organize something that we all meet also the remote speakers and we discuss with the audience there.
Okay, so
it's up to you.
Thanks, Vasek, again, and we hope we will see us soon. Thanks.
Okay, thank you very much, and enjoy the conference, the rest of the program. Thank you very much.